is kind of zooming in and zooming out, just to give you an idea of how small a nanometer is. A thumb is actually about 2 inches long. It's going to vary, obviously, different people. Football field, 1,000 times greater than that is a football field. So we're going in the wrong direction, right? Is a football field, or half a football field, 50 meters. 1,000 times greater than that is about 50 miles or 50 kilometers. 50 kilometers or 30 miles, which is it's about the size of half a football field, or the time it takes you to drive in 30 minutes if you're driving 60 miles an hour. I drove a little bit faster than that on the way here. The speed limit was 65. We're good. 1,000 times greater than that is the circumference of the Earth. 1,000 times greater than that is the distance from Mercury to the Sun, or 50 million kilometers. And this one's a lot of zeros. The nearest galaxy, 21 quintillion kilometers. What's that? There, yeah, all those zeros, way too many zeros, right? So when you look at that, the point of this is to show you that when you get further, larger and larger distances, basically it's really pretty mysterious when you look out into space, right? Pretty mysterious, and basically it's hard to comprehend that. And there are people that work at that scale. How many of you guys are going to be astronomers someday? Oh, I guess 0%. 0% of the world. Maybe. Well, okay, you are going to be an astronomer.
Well, as soon as they launch that new telescope, the Hubble is that's old school. Once they do the new one, isn't there a Hubble 2 or something?
Yeah, exactly. But
yeah.
But there's a very few, right? There's very few people that really understand that scale and size. We're going to go in the other direction now. Go down from the thumb. This is actually a picture of your hair. Okay, it's actually an electron microscope graph of your hair. Now it's obviously magnified. So you're talking about 50 to 100 microns. It's 1,000 times smaller than that thumb, 2 inches, all right, or 50. Okay. Now we're in the sweet spot. We're in the nanoscale. Anybody know? Well, this is electronics class. Have you talked about this yet?
Yeah, a little bit.
Transistor. Anybody can give me what a definition of a transistor is? What does it do?
Is the transistor the same thing as the MOSFET? That was what I was talking about.
Yeah.
What does that do?
Alright, well basically you can have a higher voltage source. I used it for like, say 5 volts in and it activated, which closed 2 other leads, which I just used to power like lights.
Cool. So
Yeah.
what does it do? It's like a switch, right?
Yeah.
This is a MOSFET here. This is what it looks like under electron microscope.
Right.
The gate is where you applied your voltage, and between the drain and the source, that's like a switch. Yeah. So.
Turning it on and off, basically. Okay. So this is in that sweet spot. Remember I said that in the definition it's 1 to 100 nanometers. So a lot of stuff goes on at the nanoscale. Right now, the transistors of today are about 10 nanometers. The most advanced 10 transistors in the best devices that you've got. Okay. Go 1,000 times smaller. Now we're out of the nanoscale. You're about basically the size of the atomic radius of the smallest atom, which is helium. You're 1,000 times smaller than that. You're in the nucleus. You're down into the size of protons. Okay, 30 protons. You go smaller than that, you're into the size of a Planck. Okay, which I didn't even know what a Planck was way back when. Now I'm getting a little understanding of it. But the more we decrease, this is the same as going in the other direction. The more mysterious and hard to comprehend things become. Right? Make sense? Well, now, contrary to there's very few astronomers, there's a lot larger number of people who are really learning to work at the small size range. And we call them nanotechnologists and nanotechnicians and so on. So that's something that you could do. There aren't a whole lot of them. So, however, there's a lot of opportunity. That's really what I'm here to talk to you about. Is the opportunity for you to be able to understand that size and scale range. Not this size, but we're talking about the nanoscale size. Okay? Make sense? This is a little just depiction of the nanoscale, if you will. And the nanoscale is this 1 to 100 nanometers, if you will, right in here. We're not talking the size of atoms. We're bigger than atoms. This is groupings of atoms. We're not talking the size of inside of the atom, the nucleus is. We're bigger than a water molecule, slightly bigger than a water molecule. But we're also in this range here, things like the virus, okay? Things like naturally, like the DNA is there. Glucose is in that range. Also, things like today's transistor, as I mentioned, is about 10 nanometers. In contrast, back in here, in 1980, those transistors that we depicted would have been microns apart, like in the 40 or 40 micron apart. And that's important, and I'll tell you why in a second, why we got smaller and smaller over time. Okay? So a couple more size things. How small? How long does it take your fingernail to grow 1 nanometer? What do you think? Any guesses? 1 hour? Huh? 23 hours? No, it's actually only 1 second.
Well, if you bite your fingernails, you'll never know.
Yeah, it's true.
It's like how many licks does it take to get inside the center of a Tootsie Roll?
Tootsie Roll, Tootsie Pop. Exactly. Yeah. You'll never know. Some people will never know. Just a couple more relationships. The reason I'm telling you this is just to get an idea of how small that nanometer is. It's really small. Okay? So, because a nanometer is to a meter. So, nanometer to a meter is the size of a marble would be to the Earth. Wow, that's pretty incredible. Yes. Okay, so these are all some other things that are on there, but I'm going to show you a quick video, because just to give you an idea. We don't have it up too loud. This one's not as fast.
Museum of Science.
Maybe it'll show you.
It'll get there. Yeah, this time of day, yeah, too much Netflix going on.
You guys aren't watching Netflix while I'm talking, are you?
No, I was back at the dorm. They're watching that new Martian movie, probably.
Small a nanometer really is. Well, first let's see how many people we can fit in this little car.
It's a cutesy thing if you get the idea.
Or what if we could shrink people down so they were just about 8 inches tall? Then we'd be able to fit about 3,000 people
This
inside
is
of
creepy,
this car.
the sounds.
But get this, if we could shrink people down so they were just 1 nanometer big, 1/1000th of a meter, we could fit every single person on the face of the earth, all 6.5 billion men, women, and children inside this car. And not only that, we could fit them inside this car.
In fact, all the world's people fit inside a car 10,000 times smaller than this little car.
So I don't know if you guys got that, but what they're saying is if we were all a nanometer in size, all of us on the face of the earth, we were all a nanometer size, we all fit inside the car 10,000 times smaller. That really helped me to get an understanding of how small a nanometer is. And it's amazing to me that we can work at that scale and size and make things like those transistors, work every time, right? So this is just a little contrast of how far we've come. Let me see if I've got that. Nope, I didn't got that. My little show and tell thing. I don't think I left it in your room, your last room. Anyway, we'll go through it.
I took a quick search. You have to make sure you have it.
I probably have it. Oh, there it is. See the guy right there? The phone from 1993, if you will. What's that? Yes, it is. It's a throwback. What else did this come with besides the phone? Anybody know?
Came with a purse.
A purse? What? Yeah. Okay. What was in the bag? Battery. How heavy was the battery pack? Exactly. Like a cinder block. Almost a cinder block, if you will. Okay, so this is not that, well, maybe in your lives it is, because I know you guys were probably born around that time. But, what's that? A little older, but not that much. Not as old as Dr. Megan, right?
Probably. Well, we started when we were like 3, didn't we?
Absolutely.
Yeah.
Yeah, exactly. I'm married 35 years, but,
Yeah.
well, that's not going to can't lie. Anyway, so you can see how far technology has come. I thought it was really cool when I first got in the shop in 2004. I said, we should take a picture of that phone and show them how far we've come in technology in just 10 years. If you look at it and say, wow, look at that, my Verizon cell phone from 2004. Well, now you start looking at some of the phones. That one's about 4 years old, I think, and that's the size of, we were talking about 16 gig basically, you know, and on the smartphones. And instead of the functionality of the 1993 phone, which was pretty amazing, look at what that 1993 phone do.
Call people.
Exactly. What can they do today?
Call people. And everything.
Everything. Okay. Well, I think it's 128 gig right now or something. That's where we're at. Really cool stuff. I mean, and you know, that's the first IBM compatible laptop, if you will. That was the first laptop computer, and it was really powerful. It had 640K RAM, right? 2 floppies, really floppies, 5.25 inch floppies. Nice. They're antiques. You can see them in museums now, right?
Yeah.
So you can get the idea. The idea is that those smaller circuits give us smaller, faster devices and more value per dollar, right? Why did we get smaller and smaller, and faster and faster? Why?
Nanotechnology.
Well, yeah, that is the answer. It's like, exactly. It is nanotechnology, micro and nanotechnology. But it's because people wanted it. Consumers wanted it. We wanted it. And nanotechnology enabled it. Just to kind of reinforce that a little bit, this is an ad, a Radio Shack ad, from, which I know is now in bankruptcy, right, I believe. But Radio Shack had that bag phone on there, and it was basically $200 for that, or $300 for that, on sale for $199. Everything on that page is about $3,100 worth of stuff. Anybody get an idea of what kind of the commonality of all those things to relate to today are?
Expensive and kind of crappy.
Expensive and well, kind of obsolete today, right? Right? You don't see a lot of people with those bag phones except for show and tell and nanotechnology presentations. What else?
CNRs is 92.
DSLRs, the VHS camera, that's still around actually.
Okay, well, yeah.
They're still at Mica, they still use them at Mica.
They still have some of these things, some of these devices. The one I was driving for was this. That all the things on that page basically are within a cell phone today. We talked about all the incredible apps. So it'd be kind of hard to carry around all this stuff today, wouldn't it? No way. You'd have to have, what's that?
Back then, yeah.
You didn't carry it around. You didn't have the portable stuff that you have today. You couldn't like enable your security system, open your garage door from right here. Oh, did I close my garage door? Well, let me close it just to make sure. And you couldn't do that from there. You had to actually physically go home and close the garage door. So, that's
On this next slide, does anybody know what this is? Me and Bob know, but what's that? It's
Gyroscope.
Huh?
Gyroscope.
gyroscope. What's it do?
You spin around and basically.
Yeah. Has anyone ever played with one of these? A few of you.
Yeah.
I've got one. I actually ordered a couple of these a while back because I surveyed my class one time and no one has ever played with one of those.
no.
Yeah. So I can see a lot of you that never have. They're really cool.
Yeah, what'd you tell him? What it does?
What it does. Well, it, as you know, is
Some of them didn't know.
the inertia. You spin this thing, the inertia will keep it vertical. Okay. It won't fall. It won't flop over. It's almost like it defies gravity.
It's like
It's
magic
really
trick,
cool.
right?
But I'll bring it in. I'll bring it in next class so you guys can play with it. If you've never played with one, you got to experience it at least once.
Absolutely.
They're actually absolutely amazing.
So this is kind of how we got to where we are today. I mean, electronics drove it. And it's through that transistor we talked about briefly earlier, that on-off switch that you've talked about a little bit in your class. And the key thing is now, in order to be able to go from that cell phone, that back phone, to where we are today, you had to get your electronics smaller and smaller and smaller and more capable and more storage capacity and squeeze more stuff into it, if you will, okay? And make the electrons go smaller distances, all right? You needed to do that. So the basics for nanotechnology came from basically the electronics industry. And this is just a depiction, a cartoon of how far apart the transistor was before, the source and the ground of the transistor, and now we're down smaller and smaller and smaller, and now you can make, instead of fitting 1,000 transistors on a piece of real estate, now you can fit billions of them on a piece of real estate. make sense to everybody? Okay, that's the journey we've been on for the last 20 years. And to me, and probably to Dr. Rankin, it's pretty amazing that we've gotten this far. It is amazing. If somebody had predicted that we're going to have a device like this, well, they did predict it, but it was pretty hard to believe that something like that was going to exist today, and just gets better and better every day. Okay? And that's not the only thing that we've got, but I'm focusing on that because it's very personal. Everybody has that capability today. Like in third world countries, they have this. It's pretty crazy. So what helped us to get there was to be able to develop tools and tool sets like characterization, fabrication tools, things that enable us to make stuff at that size. Dr. Rankin had actually studied this at Penn State. He actually worked in the nanofabrication facility. He's very, very familiar. He's an expert in this area. And he worked on these fabrication devices to make stuff, okay? And the tool sets are, how you think they're really cheap to make stuff at that size range? You're right. They're not cheap. Some of them are millions of dollars worth of equipment.
This was, how much was this? This was six figures.
This was six figures. This is about $600,000.
Yeah.
600 with the educational discount. Right, with the discount. That's fun. It is funny. And the thing about the reason why we have this program, you say, why don't we have this nanotechnology program right here at Penn College? It'd be a lot more convenient if I didn't have to go to Penn State to learn how to run this, learn about this piece of equipment, and learn how to run it and really get time and hands-on on it. That would be cool. I liked all the stuff we got here. The reason is because of that cost.
And it's the upkeep too.
It's the upkeep, yeah. The
You can't just-
$30,000 a year it cost us to actually for the service contract on this. So that's bigger than some people's budgets in some cases. So in order to do this, we have this central facility model where we pay that, and then you as a student would come there and learn the technology. Then you would go out and work, because you're gonna help the economy because you're gonna have this understanding, and then you're gonna have a great career if you have understanding of working on this. I was telling Dr. Rankin earlier that I was down in Houston a couple of weeks ago, and one of the people we're trying to start a program with there, similar to what ours is, a partnership program like ours. He went to some industry, and a guy from the industry said, "You're going to have people understand," because I have a list of skills, which I'll show you later. And he said, "You're going to have people who really understand scanning electron microscopy and how to run them. When can I have them? And how many can I have?" was the question he had. Okay, so this is one of the tools we use for characterization of the nanoscope. It's an example of one of the tools that's been refined to enable us to make those electronic devices over the years. And we have things like the atomic force microscope, which is another characterization tool that we use at the nanoscale, which is actually feels the surface, if you will. And it's one of the modes, feels the surface, if you will, and rasters across it back and forth, and then basically creates a computer image of it. It's a really cool device. I'm not going to go into the details of it, but in this particular case, this is in 1980s. People won the Nobel Prize for it. They actually moved atoms around. It's the first time they ever did that. Now you can go on the website. Have you seen this, Jeff? The Boy and His Atom.
I didn't see that.
Look that up. IBM, and they're actually now have this thing where they play Pong with atoms, basically. Wow. It's really cool.
And these things are running like what, 50,000 and less.
50 to 100,000.
Yep.
Yeah. There's some that are less.
Yeah.
If you want it with wheels, that's over 50,000.
Yeah, and you can make your own. You can actually make your own out of printer, probably.
Exactly.
Like a 3D printer. Yeah. But it won't be quite as good as this. But
it won't get down to the nanoscale, but it'll be.
What's nice is you don't need a vacuum. You don't need to suck out the air for this as much.
Yes.
You can, but you don't have to necessarily.
Yeah, for the scanning electron microscope, you need it in a vacuum. Okay. So I'm going to talk a little bit about the novel properties. I talked about the size of the nanoscale for a couple minutes now. I'm going to talk about some of the novel properties. So quick question for you. What color is gold? Gold. Okay. Good answer. Very logical answer. Gold. Just gold. Always gold. So A, who says A? Okay. B. C. We got a B. C. D. Gold. Takers. How about E? Couple. Oh, you got. Oh,
yeah.
Okay. And none of the above. Or E, none of the above. Okay. Nobody said none of the above. That's a good thing. So the answer is gold.
What is it?
Maybe not. It's both. It's gold and all of the above. And actually, the gold at the nanoscale, gold at the macro scale is gold. Okay, obviously, you cut it in half, it's still gold. Cut it in half again, so eventually you get down to these. These are actually obviously a cartoon of nanoparticles. So this might be 15. Now remember, 1 to 100 nanometers. This might be 15, 30, 45, 60, 75 nanometers. These solutions up here, the only difference between those solutions are the color of the gold nanoparticles that are contained within. Okay, that's the only difference between them. And like you said, it has to do with
size of the gold particles.
the size of the gold nanoparticles. Did I say something?
You said the color.
Oh, I'm sorry. The
Size.
Oh, thank you very much. The size of the nanoparticles, and I'm glad somebody listening to me, you're all listening, but I thank you for correcting me on that. But the only difference is the size of those gold nanoparticles. That's to me is really, really cool. What's really different, but what that also says, if you think about it for a minute, wow, the optical properties change. Okay, at that size range, but not only the optical properties size at that size change. Also, all the other properties change. And they change at each of these particular points. So the melting point for this one is different from the melting point for this one, which is different from the melting point. The electrical resistivity is different for each of these. All the properties you learn from the periodic table, or you could look up on the periodic table, or macro scale stuff, all changes at the nanoscale. To me, that's really, really super exciting. What does that say when you're at the nanoscale? From 1 to 100 nanometers, what it says is that you have not only a two-dimensional periodic table, you have a multi-dimensional periodic table. Okay? So what does that say? Okay, let's just go through this here. These are different size nanoparticles, right? These solutions, these are different chemistry. In this particular case, it's silver and gold. These are different shapes, spheres and platelets, okay? In this particular case. So think about the combinations and the permutations of all these things, and what could you make? If you're manipulating the nanoscale, it means you can make virtually anything, okay? It's pretty cool. It's really exciting if you're kind of you want to work with that scale. And people are doing it every day, and trying to figure it out. And nanotechnology has been around officially for about 15 years, if you will. 15. So you guys, in your lifetimes, 15 to the last 15 years, this is when this revolution has started to occur. You guys are really at the beginning of it. So people who get trained in this area are really at the front edge of it, and it's just going to grow. So getting an understanding of this nanoscale is really, really something that you could just think about sticking in your academic toolbox, something that you could actually have that sets you apart from other people and makes you more valuable. Make sense? Cool. And we have it. And you happen to live in a place where this is offered and was offered first, and I think it's offered, and I know it's offered the best. The other thing that you have here is, at the nanoscale, is surface to volume, okay? So the surface meaning the surface area of the volume is the same. Everybody agrees probably. The volume of this is the same volume as that. Does that make sense to everybody? Okay? Okay? In this particular case, the surface area of this, which one has the greater surface area? This one or this one? This has, let's see, this has 27 different cubes with all those different sides. This has one cube with these sides. Which has more surface area? The one on the right, right? More surface area, the one on the right, exactly. You can see right here, the surface area is actually 3 times as great. If you get down to the nanoscale, you're gonna multiply that, okay? You're gonna have to say there were those sizes of those nanoparticles. Why is that important? Why is he droning on about this? Well, the reason is because if you have large surface area, you have more chemical reactivity. Does that make sense? Okay, so one of the illustrations I like to show on that is things like silver. Does anybody know any properties of silver? Yeah, okay. Anything else? Anybody know anything about like hospital wounds and things like that? Burn victims, they usually use silver, on it because it's antimicrobial and antibacterial, and they've known that for a long time. Okay. Well, silver at the macro scale is antimicrobial and antibacterial. Well, this has a lot more surface area if you've got nanoscale silver. So now they're putting in things like clothing, okay, or in hospital rooms. because that antimicrobial and antibacterial aspect. But they don't paint the walls all silver, right? They actually put like 0.03% silver nanoparticles within the paint or within, the fabric. And that's in there and makes an antimicrobial and antibacterial. So why would you put it in socks? Yeah, okay, good. Odor. Exactly. Odor, fungus, exactly. So antimicrobial and antibacterial, that's what makes odor. Basic microbes and bacteria is what makes odor. So supposedly you could wear these, this is a Pennsylvania company that made this, you could wear these for 62 days without changing.
And then turn them inside out for another
Then
62
exactly,
days.
start over. These have been around for a while, but okay, so that's really cool. Think about that. You can put that in all your clothing. You never have to wash it, right? You never have to wash it. Pretty cool stuff.
That's right, yeah.
So that's just an example of high chemical reactivity. Things like using those characterization tools, we discovered things like buckyballs and carbon nanotubes. Anybody know anything about carbon nanotubes?
Aren't they using some article I guess back they were starting to use those things and they're trying to squeeze more extra light out of the batteries
Now they're being used in all kinds of different research for now.
They're trying to squeeze a little bit more extra energy out of the dead batteries so we're dead on the scale. They were trying to squeeze a lot more of it. This was a Canadian company that was doing it. And they were out of Toronto.
I'm not even aware of this, but I'm sure they probably are. And they're researching that. It has incredible electrical properties and also
They're extremely durable.
extremely durable, extremely strong, actually, right? Because they're like 10 to 1,000 times small. It depends on the research and the application. 10 to 1,000 times stronger than stainless steel. Okay, so you guys know what rebar is, right? Use it in concrete stuff to strengthen it. Okay, into the matrix. Well, think of this as nanoscale rebar, if you will. So you want to make something stronger and lighter weight. Anything. Things like baseball bats or tennis rackets or whatever, or golf clubs, kind of like sporting stuff. That's cool. But how about airplanes? Making them stronger and lighter weight. How about things like cars for energy efficiency and things like that? That's where a lot of these like carbon nanotubes and other materials similar to that are being utilized. Does that make sense? So that's just the tip of the iceberg. But they discovered that utilizing those characterization devices they were using for electronics. So it's kind of extended into that. Now you're in the materials area when you're talking about airplanes, if you will, the structure of airplanes. So what's different about the nanoscale? These are only a couple of the attributes in the nanoscale. Very large surface to volume ratio, geometry affects color, and physical and chemical properties change. And of course, they're very small. We talked about the attributes of why small is good. So how about some impacts of nanotechnology? Okay, so this is a prediction that said that the nanotechnology products were going to increase by 100x over 2 decades from 2020. This was made in 2011. They said they'd have $3 trillion worth of products would be incorporating nanotechnology by 2020, okay? Or about 5% of the gross domestic product of the world, and it was going to keep increasing. I'm going to tell you a little in a second more about this. Nanotechnology, you think it's new? See people shaking their head. No, not really, probably not. Remember we talked about the gold and silver? This is the Cathedral of Notre Dame. I think it was built in 1000 AD or somewhere around there. But the people who made the stained glass windows were using nanotechnology because they were using those gold and silver nanoparticles. But they were just basically doing their processing. They didn't have characterization devices that knew to be able to make it. They knew they made the color red if they did this process and used this material. Okay? Or they made the color yellow. But really what they were doing is using different size gold and silver nanoparticles to make that stained glass. They didn't know they were using it. And those things are as vibrant today as they were back in 1000 AD. Okay, this is another one similar. This is the Lycurgus cup. It has some really cool properties, very similar to the stained glass windows, but instead of, in this particular case, in reflection it looks green and in transmittance it looks red. Okay, when plastic light is transmitted through it, and they were using nanotechnology. When they analyzed it, they figured out that one of the reasons for those properties was gold and silver nanoparticles. Do you think they knew they were using nanotechnology at that time? No. This is another one, which is anybody know anything about Damascus steel? Yeah, tell me what you know.
Damascus steel was not many ancient swords that came out of northern India, southern Pakistan, and imported through Europe and the Mediterranean region. At the time, most steel, through the delivery process that was used at the time throughout the Western world, steel was by its own nature kind of on the low quality side. Smiths were able to improve that a little bit, but not very much. The steel deposits have to be processed from, like I said, I think it was India, somewhere around there, like northern Africa, something like that. The steel that, because of the precipitation of various, not only nanoparticles, but I don't want to say metal salts, but carbides, that various carbides precipitated out from impurities that were in the ore deposit at the time, were creating a harder steel before the harder metallurgy really had the ore. So you end up with these really good swords that look really good and were renowned throughout the ages.
Because they were very strong, right?
They were
very
stronger than other swords at the time. I mean, there were,
Yeah.
the legends, all with a massive steel sword, can break other people's swords, that sort
Right.
of thing.
Right.
But
Right.
they did have nanoparticles.
Yep, and that's it, exactly. But they didn't know they had it until recently, because they used those characterization devices to find them. By the way, I'm taking you on the road with me. They figured out there were nanotubes and nanowires in there. They didn't know why they had some of those properties, but they analyzed it, figured out they had those, and using those devices, they figured out what was different about that Damascus steel.
It was the last 10 years.
What? Yes.
Yeah.
2006. Yeah, exactly. Very good. So I'm going to show you a couple quick videos, and then we're going to tell you about the program, just to kind of reinforce that indeed nanotechnology is really here. I want you to observe these folks on these. See if it works. See if I was lying.
Okay, this is Neverwet Super Hydrophobic Fabric System, this particular model. We also make a paint that paints on surfaces. But with this product, you can spray it on any clothing, and it will make your clothing super hydrophobic. Water and heavy oils will just shoot off of it. Chocolates, ketchup, mustard, all of that sort of thing. Hydrophobic means that a surface is water resistant. Super hydrophobic means that the water will shoot off of a surface, won't even sit there. When you plunge this in the toilet and pull out, it remains dry. And with it staying dry, it doesn't have any bacteria on it. We made the outside of this very hydrophobic, and the center of it is untreated glass, which is hydrophilic. In other words, the center of the glass wants to attract water. The outside of the glass wants to repel water. So when we pour water in the center, it goes to the borders that we created with the hydrophobic surface, and it stops the water.
Pick that up at your local Lowe's or Home Depot. Cool stuff.
What a waste of chocolate syrup, though.
How long does that stuff last though? Because I know the spray doesn't last very long. Right?
Yeah, you know what? I'm not endorsing these products. I'm just telling you that they're. It depends on what you're using them on. They actually now have 4 different sprays for different stuff. It's really kind of cool. I sprayed the original one on my patio cushions. It wasn't the right application for it. It didn't do that great a job. Now they have a cloth.
Look, you could eat off that plunger to the right.
Now look at
Bowl of cereal.
this. They're plunging it into yogurt. Okay. You don't normally. Now see what happens when we plunge it into yogurt. You take it out.
Still the cereal.
Most people don't plunge.
Sounds like a rough morning. Huh?
Yeah, most people don't plunge it into yogurt, though, right? Did they do?
Well, but there could be some things, consistency of yogurt, especially especially eat over at the dorm cafeterias.
Ooh. Okay, one more, and I'll move on.
This animation depicts Keystone nanotechnology that treats cancer more effectively than current therapies. Keystone Nano is building on technology developed at Penn State and the Penn State Hershey Medical College. Keystone Nano assembles nanoparticles containing a therapeutic drug. With trillions of particles per ounce, an IV solution packs a big punch. The nanoparticles circulate in the bloodstream. Their structure and size, which is much smaller than a blood cell, allows them to travel in the body longer than free drugs. To support growth, tumors create blood vessels to supply nutrients. But typically the vessels created by tumors are poorly constructed and provide small gaps to access the tumor. Particles slip into cells and selectively kill tumor cells and shrink tumors. More information is available at KeystoneNano.com.
Okay, so my point here is to show you that on this slide here, there's another one, I won't go through it, but there's another one that shows the efficacy of this filter too. It's a nano aluminosilicate filter, basically, filter media, and it filters down to the,
I think you got the other
I did it probably.
the YouTube video going.
I think it just kept on going.
Yeah.
I don't know what it's showing, but. Oh, it's actually in Spanish.
Yep.
Maybe that's not it. Oh, was that it? Yeah. Okay, good. Let's go back to that. Oops. Okay. So my point of this is to show you, this filter basically filters down to the nanoscale, okay? And actually it could be used, they have it showing using a pump with this filter on it, pumping out of one of the local rivers up at Scranton basically, and the guy drinking right out of it. And instead of not treating the water or doing whatever, you could do it for that, but you could also use it in third world countries for cleaning up stuff. And actually the company that's making it, I talked to him just actually a couple months ago, he said, the sales of that are going incredible, and it's for huge systems, not just water bottles and things. You can buy those at Walmart or whatever, and you'd have to make sure you have the right ones that filter down to the nanoscale. The point of this is that all of these applications are within 100 miles of here, basically, or State College or this area, and I could have had way more, but I just wanted to show people that nanotechnology is real. It's in their backyard, and it's being made here by small companies and large companies. This company was not making sprays for Rust-Oleum or anything like that, or nanoscale, this never wet stuff. They were making metal products. They had a government contract that needed stuff for super hydrophobic, where the water would flow off. And these discoveries were made by a scientist, and they got into the business, and then they sold the technology to Rust-Oleum and actually to Rubbermaid, if you will. And there's stories like that all the time. People are adapting into the nanotechnology nano regime. Not going to go through these. I'm going to move on. These are
So the drill sergeant one, I guess the guy had the never wet on, and
now that you say that, I have to show.
I was going to say I'm
I have to
curious.
show this one. I have to show it. I do like that. Is actually my favorite. I'm going to show it.
This looks
because-
funny, yeah.
Have you seen this one? Anybody seen this?
No, right up the lay up.
Another nano one.
Every one of you, come through my mud pit today. Every single one of you put your heart on the line, did you not? Yes, sir. I can't hear you. Yes, sir. A little bit of mud makes you. Jiminy Christmas, little princess, white dress. Look at you. What's your problem? Didn't I send you through enough mud puddle? Sir, yes, sir. Didn't you do push-ups and sit-ups in the mud? Harder, 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 faster. Sir, yes, sir. Did you go through my tube? Did you run through my tires? Sir, yes, sir. How are you so clean? Sir, never went, sir. I don't believe it. Because of you, you're going to do it all over again. More push-ups, more mud, and every one of them are going to pay the price because of you. Every one of you getting on my pit. Now go! I love the smell of never wet in the morning. Oh, that water. Oh, that water. Never wet. Never wet.
Okay, well, anyway, there you go.
And there you go. All right, who knows the reference? I love the song. it was Apocalypse Now.
Oh yeah.
I love the smell of napalm in the morning. Anyway, so you get the idea. They're out there, and these applications all over the place. And just to illustrate, this is a slide that I saw a couple years ago, and this is just to show that the idea is that you can look anywhere and see nanotechnology. This is about 5 years old. So some of the things that are in this picture are actually obsolete, okay? But they're there. You know, nanotechnology is kind of everywhere, and you can just find it anywhere. This happens to be a square in Germany, Stuttgart, Germany, apparently. So anyway, you can see that, but in this classroom, we've got tons of nanotechnology right here in this classroom. You agree with that? Yeah? Okay, cool. So where's nanotechnology used? Well, semiconductors, electronics, pharmaceuticals, chemistry, polymers, materials, medical biotechnology, and kind of anywhere you can think about in every industry sector is utilizing that. I just gave you a few examples here today, okay? So the idea is that getting this training makes you more diverse in your work, not only in your industry, but in any industry, because you're gonna have this skill set. The idea, the NNI wants people that could actually, they want this revolution in technology that benefits society, if you will, at the nano scale. And they want, what they want, or it's simple, they want a lot of research and development in this area. They think there's exciting things. They're investing lots of money. All these, our government is in, all of these agencies have nanotechnology initiatives. There are people that will come through a program, work at NIST, or work at NSF, or work at different places. They work at national labs because they have this skill set. So you too could potentially be one of those people. They work in, they also want products. Things like some of the products we saw today. They want products to come out. Now that keeps the economic engine going, if you will. And then they also want, they need infrastructure, okay, to enable to make those products, but they also need things like that, those characterization and fabrication and clean rooms and so on. But they also need a skilled workforce, and that's where you guys might come in if you were interested in this.
Yeah, Bob. Also, in the past, the students while they're still in school was what they call them REUs, the research.
Yeah. Oh, yeah. That's a great.
Yeah, the students that go through this, if over the summer there's grants given at like the Sandia National Labs and stuff, right?
Yeah.
Students that have this background.
And other
Yeah.
colleges too.
Yeah, maybe you know more about that.
Yeah,
than
I can tell you that these REUs are really cool, and they're actually for both associate level student. You might be an associate level student in this program, or you might be a baccalaureate student in this program. They give REUs to both. Okay, and you go in there and you learn about how research works. Okay, you go and you work in a laboratory in a national lab, or you work in a university research area. You might not have an idea like something I think I'd want to work in. I want to work in one of these labs someday. I think that would be really cool to be either doing research myself or supporting research. That would be really cool to do that. So they have REUs to learn about what that's all about, and they basically pay you to come.
Yeah, it's research experience for undergraduates.
Research experience for undergraduates, and it's very competitive. Okay, you have to go for it and get good grades and things. The thing that helps you with your competition immensely, because a lot of them are working at the nanoscale, is going through a program like ours. So people who have gone through our program, and if they're thinking about REUs, they really are at the top of the line because they have everybody else has the basics. They have the chemistry, or where they have the electronics, or whatever area they might be in. Okay, the people that have this skill set are very unique, and that puts them right at the front of the line and we've had great success of placing people
Right.
in REU.
And there's housing stipends. They
They
pay,
$6,000, $7,000 a year, or whatever it is, or
plus they get
a
paid
summer.
a summer. Yeah, I mean, you get the stipend for housing. I think there's even for food allowance or whatever.
Yeah.
I mean, it's pretty good. It's like as if you were making $12 an hour full time during the summer. You can actually go do an REU and you get paid about the same, but you're not where you're working. You're
Yeah.
just shadowing a researcher. I mean, Penn State, you guys do REUs,
Oh
right?
yeah, we do REUs. So you could go to Penn State, you could go up to Cornell.
So you bring in students from other parts of the country,
all over the place.
and it's kind of grant supported. You don't really have to
Yep.
pay necessarily, right?
It's actually like an internship type thing,
Right.
Because you're learning about. Suppose you potentially want to go to graduate school or something like that. It's a great way to get an understanding. I think I want to do research. I want to go in this, even if you don't go here, but you really should, like, taking your summer and trying to figure that out, if it's right for you, is really important to do that. And in that particular case, if you can get into these, it's a way of you looking at them, saying that's what I want to be doing, or looking at the job and saying, I think I want to go to Penn State and I want to be in this, and then you go there and say, that's not really for me.
Yeah.
You're finding out in the summer is a lot better than finding out when you're in your career.
Yeah.
With your career.
Right.
It's a
And,
really
and,
good
and the
idea.
professors involved get cheap labor.
Yeah, oh yeah.
Or free labor.
But they love having somebody
Yeah.
that comes through this program
Because they do
they're
real-
ready to get some work.
Yeah, they do real research stuff that they get results that these professors can put in their papers and go to conferences. As
And,
you know.
there are people who've gone through
Yeah.
our reviews and ours that have gotten their names in papers, which is really great if you're a entry
Exactly.
level.
So I know Charlie was interested in we were talking about that Penn State, but this is kind of a good way to get yourself hooked in to main campus, and not just at Penn State, but could be somewhere completely different.